I'm going to speak with you today about browser graphics under the hood. What does that mean? This is what happens in the browser while we as front-end developer try to run our application, try to move things around, try to animate, try to change our content. The browser is doing all kinds of secret things underneath, all kinds of hidden things. Now, why did I get under the hood in the first place? I was working on C++ UIs, on mobile, on TVs. At the time where the world was moving from native to web and back to native and back to web, nobody was really sure. At the time, people were saying web is slow. HTML5 is slow. Animations are bad. I had all those big categorical statements I had to deal with when looking at web. As someone who grew up on detective stories like Agatha Christie, I don't like mysterious statements. So I went into the code myself of WebKit and saw what's going on there with animations and found that maybe animations are slow, but the code is there and maybe we can fix it if we understand what's going on there. So even though I had that long curly hair from Christian's photo, I got myself under the hood and didn't mind it getting all smoky. Okay, this is why I got under the hood, but why should you crawl under the hood? So imagine front-end development, you guys, all of us, as car drivers. We drive our cars, we shift our gears, we press the gas and the brakes. We can get from point A to point B without understanding the engine. However, several things can happen. First of all, you might not get the best gas mileage, all right. Second, when you go to the mechanic, he can rip you off. I know that because I've been a browser mechanic. Third, you're not just drivers, you're professional drivers, you're professional front-end developers. There's not always a browser expert. You can get stuck in the desert with your car broken. You can get stuck with a deadline and you have to fix your slow website and there's no one to ask. So this will give you a tidbit of how the browser works internally so you can make informed decisions. The first part is going to be rendering pipeline 101. I'm going to explain about the different pieces of the browser rendering engine. I'm going to use terms that are used in the Chrome DevTools. So every term I use here, I didn't make it up. You can go to the Chrome timeline and see it later, see what the browser is actually doing. Specifically Chrome, other browser engines use slightly different terms. So the first part of the rendering pipeline is style. In Chrome, this is called calculating style. If you look at the Chrome timeline, that's what you're going to see. So I wanted to explain what that actually means when Chrome is recalculating style. So at that point, what Chrome is doing, or the browser engine, is taking three main things that you have control over as front-end developers, and also the user have some control over. So those three things are the DOM, the HTML, the semantics of the tree, CSS, how you chose to set up your style rules, and the state. What I call here the state, one is, you know, the media, which device you're browsing with, and also hover, what's going on with the user, where is it scrolled. So when we calculate style, we get for each element separately its current style properties. We can also reach that in JavaScript with getComputedStyle. The second one we hear about a lot is layout. We hear maybe layout is bad, avoid layout, or reflow in Mozilla. Layout is a very important piece of the web. Let me explain how I look at it. So what layout is in charge of is setting up absolute geometry, taking each element and deciding where exactly it's going to be and how big it's exactly going to be. So it does that by rules. Okay, so we have the rules, we have the percentages, We have a Flexbox. We have all kinds of inline stuff, like the floating images, a whole bunch of text rules with the spacing and the wrapping. All those are layout rules. Now, the layout is a heavy operation. It takes all those rules, takes the content, and turns them into absolute positioning and absolute size. One thing people ask themselves sometimes is, why not just take every element and give it the absolute size instead of applying rules? Take every text we have, we know how it's going to look like. Let's decide where it's going to be. Take every image, decide exactly where it's going to be. The answer for that is that layout deals with the unknown. We have two main things that are unknown in the web. One is the content. We can have data coming from a blog. We can have data coming from a database. We can have text that the user just entered. We can have all kinds of images, videos. Those are unknown at the time the front-end developer is in charge. So we don't want to set up absolute positioning for every type of content that might be out there. The second thing that is unknown is the viewport. We don't know what is going to browse us. So it can be a mobile phone or desktop computer with Internet of Things. It could be a refrigerator or a watch. And we have accessibility, so all kinds of browsers with different abilities are going to see your content. This is, to me, what makes the web beautiful. It's dealing with the unknown. Again, as somebody who came from detective stories, that's what excites me about the web versus working natively with apps. Everything is unknown. So the layout is an important piece that takes a lot of unknowns, put them together with rules, and make them into absolutes, into where things should be, how big they should be. The next phase is paint. This is actually a lie. It's not the next phase, but it used to be the next phase in the browser up until a few years ago. How paint works. We did two things so far. Each element decided on its styles based on the style rules, on the DOM, and on the state. We calculated where everything should be and how big it should be. That's the layout. Now, for each change that happens in the page, we check what has changed, which area has changed, and we tell the browser to repaint it. So this is how browser used to be. You change text in some areas, the browser will say, okay, I need to repaint that area. Now, when that happened, we had this problem. You see the text and the bunny behind it. Every time the bunny moves, the area in front of the bunny also needs to be repainted. We have to paint the grass and the bunny and the text, the grass and the bunny and the text, because they are on the same area of the screen. Not just that, we have text here with glow. This is a heavy operation, a slow operation. Keep doing it. This is why several years ago, the browsers introduced compositing. Compositing is to painting like paper cutouts. So instead of drawing the bunny and the grass and the text over again for each geometry, we take paper cutouts, we put one of them with the grass, one of them with the bunny, one of them with the text, and we just copy them each time. So this is what happened when we see compositing. What actually happens in the computer, in the browser, is that we save memory for each of those layers. We take the size of the bunny, we allocate memory to it, and we paint the bunny into that. We take the text, and we paint into that. So the same way, using paper cutouts will take you more resources, will take you more paper. Compositing might get us to paint less, but it will cost us more memory. So Nothing comes from free. Now, another thing that was introduced together with compositing, actually in Microsoft it was, in Explorer it was introduced a little earlier, is painting with graphics accelerator, with the CPU versus the GPU. Many times we hear things like, use the GPU, it's better. Use the GPU more, the GPU is faster. So this is not actually true. The GPU is not faster than the CPU. I like thinking of the CPU and the GPU as a single Jedi versus 1,000 stormtroopers. Each one can do different jobs differently. A stormtrooper or 1,000 stormtroopers are probably a better choice when you have to cover a whole desert planet and look for a lost droid. Each one of them will take a little area, will scan it in a silly way until one of them finds a droid. However, if you have to smuggle secret plans of a spaceship without anybody seeing you, maybe you're better off with one or a few Jedis. The same goes for CPU and GPU. When we have to draw text, for example, text is complicated. We have to deal with the fonts. We have to deal with all the spacing, all the wraps. In the example before, you saw a glow. All of that is fine work. It's work for the CPU, usually. However, when we have to take big images over a large set of pixels and just copy them, maybe do some blending, maybe rotate them a little bit, that is a much better job for bulk operations, for the GPU. So when we look at a scenario like this, when we have text in front of a moving image, usually we would prefer to make paper cutouts, use the CPU to draw the complicated things, like the text with the glow, maybe the bunny if it's SVG and has a lot of paint commands in it. And then we use the GPU to move around those paper cutouts, just copy them and blend them with what's behind them if they have opacity. This is empty. Okay. I'll go back to it and say what was supposed to be said here. So, what was supposed to be here is that the key to graphics performance is concurrency. We didn't see quite why yet. One part of it comes automatically from using the GPU. The way GPU works is that it has thousands of cores versus just a few we have in our CPU. So what bulk operations do is that we prepare the GPU, and then it goes to many cores at the same time, and they just cover grounds with mathematical operations. We have another way in the browser to achieve concurrency. How do we usually animate things, change style? Usually we just get some sort of a timeout, either from request animation frame or from set timeout, and we change things. We change the style, right? So, yes. So when we do that, we are not concurrent. We are using JavaScript, which means we are on the same thread as everything else in the system. Decoding images might happen on the same thread. JavaScript garbage collection. Even if your JavaScript code is amazingly fast, something else can still hold you in the queue because you're not concurrent. The nice thing about compositing is that it has its own clock in some browsers that works in the background. So when you tell the bunny, just move over there, all of that can happen in a different thread and cannot be bogged down by garbage collection or anything else in the main thread. So as you saw in that white on white previous slide, concurrency is key. Now I'm going to show you how all this works in a real, completely curated for this demo scenario. This demo is available on GitHub if anybody wants to look. Anybody remember the game Lemmings? Yeah. Yes. So we're going to drop Lemmings because that's what they do. We're going to use, let me explain about how the screen is built, okay? We have different ways to drop it. Each time it's going to be dropping and looking the exact same way. However, the rendering pipeline of the browser is going to do this differently. And we're going to explain why, how to debug it, and when it's a good idea to use that technique of the rendering pipeline. On the other side, we see what we are actually doing when we prepare, meaning once for the whole animation. And we're going to see what's going to happen for each frame, what code we're going to run, and what the engine is going to do. And I know I have the Chrome DevTools open on the right. We're going to use it in a moment. So we start with layout. I'm sorry that it's a little pixelated. I'll explain the code itself. What we are doing here is that for each frame, we change the margins of the lemming. We changed the margin left and margin top. So it still animates the lemming because its margins are changing. But what happens with every frame is a lot in the engine. First of all, we get to request animation frame, so we have to wait for the main thread to clear. Then we calculate the style because we changed the margins. So we have to calculate the actual style of the lemming. Then we have to use layout. That's because the margin is a layout property. It affects the rules, it affects everything around it, it affects inlines. So every time we change margins, we have to layout. And then we have to paint, probably with raster. Raster is a different word for the CPU. Raster actually means turning graphical objects into pixels. But in this case, in the Chrome DevTools, raster means you're using the CPU. Now, if I use paint flashing in the Chrome DevTools, you see that we paint around the lemming and the lemming itself and probably the whole scene over and over again. This is very inefficient. We already know how the lemming is going to look like. Painting it over and over again is not going to help us too much. Now, when should we use layout? We should use layout when we have rules, when we have changing content. Here, for example, the layout affects the width of the scene, so it's going to affect the width of everything. So we have a whole bunch of rules applying for each frame. If we had to calculate all of that by ourselves in JavaScript, we would probably want to be that lemming and fall somewhere. So layout might not be good when you know what's going on, when you know where the lemming is going to fall. But if a lot of things need to change as a result, if you have a whole bunch of rules that apply as a result, maybe layout is something we can consider. Next one is translate 2D. This is a little better. It's not that bitter. You see that I'm pointing on the screen, but you can't see it. We are seeing that the lemming itself gets repainted, but not the canvas around it. What we do for each frame here is that we set the transform of the lemming and nothing else. So we still recalculate the style, we still request the animation frame, and we still paint. One thing we did not do here is layout. So when we just move things around, regardless of the whole page, regardless of how the whole page reacts to that, if we have something that is separate from the page, that moves separately from the rules of the page, transforms are nice because they are not a layout rule. They are just a rendering rule. However, we still had to paint the lemming over and over again. For this, we have the nice new property called will change. You see here, we do not paint with each frame. What will change does is cut out a piece of paper, cut out a piece of memory, call it a composited layer, paints the lemming into that, and then it will just use the GPU to render to copy it over and over again as a bulk operation. You see in the code that we prepare it by telling the image that it's going to change its transform. That effectively makes the browser composite it, prepare a new layer for it, prepare a new memory for it, and make it so that the GPU can easily copy it over and over again. So what we do in the engine with each frame here is that we still request the animation frame. We are still bogged down by the main thread. We calculate the style because we are changing the transform, and somebody needs to deal with it, deal with all the inheritance in CSS, etc. But at the end, we composite. We give rules to the GPU, to the compositor, and it's going to do the heavy lifting of painting thousands of pixels for us. We don't have to do all of that by ourselves. Now, if this is the case, if will change is so nice, why not use it every time? I've seen as front-end developers and somebody who worked with front-end developers, many times we do that trick of translate Z0 on things. We hear, usually the phrase is, somebody told me that if you put translate Z0 on an element, it's going to be better for performance. I think that's about the phrase people hear. So, first of all, will change is in any case a better choice because it tells you what's going to happen. However, all that it does is a paper cutout, new memory. Where it's not good, it's here. You see that we have changing numbers on the lemming, which is the X and Y of the frame. So the lemming anyway has to redraw itself with each frame. It has to draw new text with each frame. So putting one version of it on a cutout is not going to improve performance. We have to, with every frame, paint into the cutout, into the layer, and then paint the layer on top of what's on top of the canvas. Doing this together with will change is actually bad practice. So what did we learn here? We have to pick our optimization flags like will change and translate based on what's actually going to change, based on the predictability. And the next two ways to drop a lemming are a little bit different. They use the Canvas APIs. So how many of you have dealt with Canvas and or WebGL? Some. Yeah. So with Canvas, it's very interesting because maybe we can't see the colors from over there, but we draw the canvas with every frame. It's a big paint operation every time, with every frame. We request an animation frame and we paint. However, there are two things we do not do here. We do not calculate the style and we do not layout. So actually we are doing something that the browser is going to do anyway, which is painting, and we do it all by ourselves. We work around, we bypass the browser rendering engine and do it all by ourselves. In this case, with every frame, we have to clear the canvas rectangle. If we didn't do that, this is what it would look like. Now, when we want to achieve effects like that, you cannot do them with CSS. You cannot just move the lemmings. So when you have to achieve interesting, I don't know if that one is interesting, but if you want to achieve 2D effects that CSS doesn't support, Canvas might be a good option. The next one is WebGL. So here with every frame, we draw using GPU commands. And we prepare the lemming by making it into a GPU texture with OpenGL. We prepare a lot of geometry. One thing about WebGL code, if you ever wonder how to draw simple images in WebGL without libraries like 3D, this is how you do it. I think this is the minimum amount of code you need for that. Maybe I have 1 or 2 lines that I don't need, I'm not sure. So GPU requires a lot of setup. And we don't want to do that when we have to set up over and over again, when the text change, when the images change. So here we set up the GPU once. And with every frame, we just tell the GPU to clear and draw in different coordinates. So again, this is a little like Canvas, where with every frame, we paint, only this time with GPU commands, which is better for bulk operations. Where is this good for us? When we want to do 3D effects. You can't really achieve these 3D effects or better ones. I'm not the best WebGL developer, maybe in this room. You can achieve 3D effects that you cannot simply do with CSS. So that's when you want to use WebGL. The last one is CSS animations. We just set the CSS animation on the lemming. From a painting perspective, this is very similar to wheel change. You see, we don't paint with every frame. All we do is let the engine composite and decide where the lemming is going to be, where the cutout is going to be copied. One very important performance thing about CSS animations is that it does not have code for each frame, meaning that we do not have to wake up the main thread. So if there is heavy garbage collection, the browser is doing something silly, all kinds of things can happen, and the animation would still look nice if there are CSS animations because of the compositing running concurrently in the separate threads. Hence, concurrency is key. When do we still want to use will change with JavaScript? For example, if we do not know what's going to happen, if, for example, it's based on the mouse movements, then we need application code for each frame anyway. If we need application code and decision making for each frame, we want to use JavaScript and not CSS. So, takeaways. Magic out, analysis in. Analyze your pipeline. Know when you have paper cutouts. Understand what is done by the GPU or the CPU. The Chrome DevTools, timeline, rendering helpers, and the other browser. I'm just more familiar with Chrome personally. Are your friends to analyze what's going on. Plan your rendering strategy. Understand if you're going to use layout rules, flexbox, etc., or you're going to use transforms, or you're going to use animations directly. Performance, frame rate is not the only thing. Consider threading. You can be bogged down at areas, and also consider memory. Every time you have those translate Z zeros and you cut out new pieces of paper, you're using resources. This is the closest I got to a cheat sheet. The rule of thumb is predictability. Try to predict what is going to happen, what is going to be dynamic in your page. Your content or media are unpredictable. This is what layouts are for. They are for unknown content and unknown media. Media meaning which device you're using. You have unpredictable motion. Things can move around based on the mouse, based on application, based on intelligence. Use JavaScript and transforms. You want all kinds of effects, 3D effects, 2D effects that are not just changing a little bit of elements. That's what Canvas or WebGL are for. If we are predictable, we know what's going to happen, CSS animations are usually a good choice because they let the browser be more concurrent. Thank you very much.